To monitor server health or track user behavior, system engineers must analyze billions of queries continuously streaming through their networks. We rarely have the computing capacity to capture and process the absolute entirety of that data. We are forced to extract isolated fragments, small samples taken at specific moments in time. When we map those isolated fragments, we are using descriptive statistics. This is the mathematical process of summarizing only the raw data we actively hold in our hands. If 106 out of 200 polled users report a system error, our sample proportion is 0.53. In statistics, this single number is a point estimate, a solitary numerical value used to estimate an unknown population parameter. To bridge the gap between a tiny sample and the massive true population, we use inferential statistics. This allows us to mathematically estimate the parameters of the whole network based on that single point estimate. While descriptive metrics summarize observed events, moving toward a predictive model of reality requires a framework that can calculate the specific weight of what we haven't seen. The first step in building that engine is finding the center. Metrics like the mean, median, and mode provide a basic anchor point for any dataset. However, the center is only one dimension of the data. Without knowing the dispersion, or how widely scattered the data points are, the mean alone cannot tell us if the system is stable or prone to extreme outliers. Consider these two dot plots showing student marks on two different tests. The centers are nearly identical, but the spread of the results is significantly different between the two groups. We calculate the range by subtracting the lowest observation from the highest. Test A spans from 45 to 70, giving a range of 25. Test B spans from 45 to 65, for a narrower range of 20. While range identifies the boundaries, variance is the robust metric that calculates the spread of all data points. It tells us exactly how much the individual scores deviate from the average. A mean locates the data, but variance provides the mathematical context required to determine the reliability of that location. To model this spread systematically across complex systems, engineers use random variables. These are numerical values tied directly to the outcomes of a random phenomenon. When we are tracking exact, countable events, like the precise number of defective server components in a batch, we use discrete random variables. This bar chart represents a discrete probability mass function. To find the total probability across multiple outcomes, we sum the probabilities associated with each possible value. When we know the mean number of events occurring over a specific time interval, we apply the Poisson distribution to calculate the probability of a specific number of occurrences in that space. However, measurements like network latency, physical weight, and processor temperature can take any value within a range. These are continuous random variables. Because continuous variables have infinite possible fractions, we shift from discrete summation to calculus-based integration, using a continuous probability density function. By integrating that function from negative infinity up to our target value of x, we calculate the cumulative distribution function. This identifies the total probability up to that exact measurement. The fundamental nature of a variable, whether it steps in distinct counts or flows continuously, strictly dictates the mathematical tools required to analyze it. Even with the correct formulas, taking isolated samples creates a persistent issue: sampling error. Every time we repeat a sampling process, the calculated mean will change slightly. If we map the distribution of these constantly changing statistical values, we create what is known as the sampling distribution. This distribution is governed by the central limit theorem. The theorem applies when the sample size is large, which is mathematically defined as n being greater than or equal to 30. This is a simulated population curve. It is highly asymmetric, jagged, and entirely unpredictable. If we extract random sets of at least 30 data points from this chaos and plot the calculated mean of each set on a new axis, the distribution of those specific sample means will naturally arrange itself into a symmetrical normal distribution. If the sample size is less than 30 and the population variance is unknown, engineers substitute the normal curve for W.S. Gossett's t distribution to account for the increased uncertainty. The central limit theorem allows us to assume normality in our estimates, regardless of the distribution of the underlying population we sample from. Because the central limit theorem produces a predictable normal shape, we have the mathematical basis required to estimate unknown population parameters. A single point estimate, like our initial system error rate of 0.53, is a solitary guess. On its own, it provides no information about how reliable that estimate actually is. Instead of pointing to one number, we use interval estimation. We construct a set of real numbers between two values calculated to contain the parameter. We attach a confidence level to this boundary, the calculated probability the interval contains the true population parameter. Interval estimation transforms a single numerical guess into a probabilistically bounded range, explicitly accounting for sampling error in the final result. We apply this same logic to more complex engineering problems, such as estimating the total variance across an entire population. This establishes the confidence interval for a single population variance. The true variance is bounded by two fractions utilizing the chi-square distribution. The calculation relies on statistics we already gathered. N represents our sample size, and S is the sample standard deviation. Calculating a 95% confidence interval using this formula implies the methodology generates an interval containing the true parameter 95% of the time. These intervals provide the mathematical bounds necessary for analyzing user traffic patterns, benchmarking server performance, and refining the models used in machine learning. By mastering variance, continuous probabilities, and the central limit theorem, engineers convert raw, incomplete data into precise predictive science.